Hey everybody, welcome to the Grignard lab. Here's the outline for this video. I'm going to be going over the reaction for a little bit because some of the conditions and the procedure are pretty specific, especially when setting up this reaction. So I'll be going over that for a little bit. Then I'll talk about some concepts in IR spec, take a brief look at one of the NMRs, and then I'll show the actual experiment in the lab. Here's the reaction that we'll be doing. We'll be taking benzophenone and reacting it with the Grignard reagent, which we'll be making in situ to form the triphenylmethanol product. Initially, we'll need to make the Grignard reagent by reacting magnesium with bromobenzene, and then we can introduce benzophenone to form an ionized product, and upon introducing an acid, the alcohol product is then formed. For the first step of creating the Grignard reagent, and throughout the process, we need to be careful because it is highly reactive with water. It is an incredibly strong base, and if water is introduced, it'll react with the water instead of benzophenone and form benzene contamination. So before the reaction, we'll be drying all of the glassware in an oven and adding a lot of the reagents to the round bottom flask using a needle and syringe. Also, bromobenzene should be added slowly dropwise to control the formation of biphenyl contamination. If it is added too quickly, it'll react with the Grignard reagent forming and create this biphenyl contamination, which we'll be checking for in the experiment using a TLC plate. While adding the reagents, we'll be looking for the formation of small bubbles. This is an indication that the reaction is happening. We'll be introducing a small amount of dibromoethane because it chemically activates the magnesium metal. It reacts with the magnesium to expose a clean reactive surface, which can then react with bromobenzene. And throughout this process, dibromoethane turns into ethylene gas, which we will then observe coming off as those small bubbles. After all this, we'll expect to see the solution end up as a brownish gray color, indicating that things are going well. After about 15 minutes, the benzophenone will be added dropwise, and at this point the solution should turn a magenta color, like a dark reddish pink. If this doesn't happen, that means something went wrong and we would have to start over. As the reaction progresses, the salt product will begin to precipitate out of solution, as was shown in the mechanism, and as this happens, the solution will lighten and eventually turn completely white as the salt product forms. Once done, we'll add some HCl to protonate or hydrolyze the product, which will move it into the organic layer. But the HCl will also react with any unreacted magnesium, which will slowly dissolve it in the aqueous layer while releasing off some hydrogen gas. The round bottom flask will end up looking like this, where the organic ether layer containing the product is on top and the aqueous layer on bottom. We'll remove the aqueous layer to a 5 milliliter conical vial and extract it 3 times with ether. Then combine all of the extracts and dry them with sodium sulfate. Here we can check the purity using TLC, and this is where we'll be checking for the biphenyl contamination. So we'll spot a TLC plate, and if it's a pure product, we should only see one spot after it's developed, but if it ends up looking like this, the top spot would be for the biphenyl contamination, and we'll have to get rid of that somehow. The ether solvent can then be evaporated and the crude product washed with Legroin. Now the product itself is insoluble in Legroin and will remain as a solid, but biphenyl will dissolve, and once we remove the Legroin, that should also remove the biphenyl contamination. Then the product can be recrystallized using ethanol, but we do want to be careful here. We want to be careful not to boil the ethanol. In most cases, when performing recrystallization, if too much solvent is added and the product is having difficulty coming out of solution, we could simply boil off some of the solvent and that would do the trick. But in this case, since we used hydrochloric acid earlier, there's a chance that there's still some left over, and if the product is introduced to a bath of ethanol, an acid catalyst and some heat, a byproduct could be formed during the recrystallization process. So if too much ethanol solvent is added and we're having trouble getting the product to come out of solution, instead of trying to boil off some of the ethanol, instead we can add a small piece of ice. Since water is miscible with ethanol, this will increase the polarity of the solution and decrease the solubility of the product in that solution and can help the product come out. Then once we have the recrystallized product, we can characterize it by taking a melting point and running an IR spec. Now, the IR for our product, the triphenylmethanol, is actually going to be slightly different than we might expect. For most molecules containing alcohol groups, we're pretty used to seeing a fairly wide peak on the IR spec, and that actually comes from hydrogen bonding between the molecules. Hydrogen bonding broadens the peak for the OH group. As the OH groups hydrogen bond with each other, this weakens the bond between the hydrogen and the oxygen that is covalently bonded to. And there's a lot of variance in how tightly bonded each hydrogen is to its respective oxygen. So there's going to be a wider range of infrared light being absorbed by each of those OH groups. But if we look at a molecule like triphenylmethanol, where the OH group is a lot more sterically hindered and therefore can't hydrogen bond nearly as well, we see a much sharper peak for the OH bond. And that's because there's a lot less variance in how tightly bonded that hydrogen is to the oxygen. Finally, I just want to go over something real quick for one of the NMRs. So if you look at this one here, and you were to have completed the NMRs for the other two compounds already, you would be left with the Grignard reagent for this one. But if you were to run it in an NMR, the magnesium would actually do some really weird things to the chemical shifts. So the NMR was run with bromobenzene instead. So when analyzing this proton NMR and the carbon NMR, use bromobenzene and not the Grignard reagent. I'll start by drying all of the glassware in the oven. So this will include the round bottom flask, the spin bar, Claisen adapter, and the drying tube, and I'll leave it in there for about 15 minutes. I'll want to polish the magnesium metal before using it in the reaction, so I'll be using a mortar and pestle to do that. Once that's done, I'll weigh out 54 milligrams of the polished magnesium, add it to the round bottom flask, and finish setting up the apparatus. Then I'll add 250 microliters of anhydrous diethyl ether, which is dry diethyl ether since we're being careful of not having water contamination, and I'll add that through the septum into the flask. 2 drops of dibromoethane are now added to react with the surface of the magnesium, and we'll watch for the small bubbles a little bit later. The bromobenzene solution can now be prepared, so I'll add 220 microliters and mix it with 800 microliters of anhydrous diethyl ether. And I'll be adding about 6 to 8 drops while checking for the formation of the bubbles. And I'm not seeing any right now, so I'm going to go ahead and add the rest of that solution to see if they form. Still nothing yet, so I'm going to go ahead and rinse that same dram vial with some more anhydrous diethyl ether and add that to see if anything changes. If you look at the round bottom flask while I'm adding it, you can see the bubbles starting to form, so that's a great sign that the reaction is now happening. So we'll let that react for 15 to 20 minutes, and in the meantime start preparing the benzophenone solution. I'll weigh out 273 milligrams and add it to a dram vial where I can dissolve it in some ether. I'll add 800 microliters of anhydrous diethyl ether and shake it up until all of the benzophenone is dissolved in the solution. Now this solution can be added dropwise to the flask, and this is where we're expecting to see the pink color, which we can clearly see forming here, so that's great. That means we don't have to restart the reaction. I'll finish adding all of that solution, then rinse the dram vial with some more diethyl ether and add that to the flask as well. As time goes on and this continues to react, we'll start to see the salt product coming out of solution in that white precipitate, and the solution will continue to lighten as the product forms until what's left is just a completely white solution. Once there, we are now ready to hydrolyze the product using an acid. So I'll get some 3 molar hydrochloric acid, and I'll continue to add this until the solution is acidic. This means that the product should be completely hydrolyzed. While it's being added, you can see hydrogen gas being released as the acid reacts with the magnesium. And I'll mix the layers together really well, making sure that all of the product interacts with the acid. After a little bit, I'll check the pH of the solution, and it's definitely acidic, so we should be good to move on now. I'll remove the spin bar and then move all of the aqueous layer into a conical vial where the extractions can then be performed. To do those extractions, I'll be using some more diethyl ether. And again, diethyl ether is less dense than water, so it'll be on top of the aqueous phase. And I'll go ahead and do 3 of those extractions. Once those extractions are done, I'll combine the extracts with the original ether phase from the reaction and dry them all together with some sodium sulfate, and I'll add that until it's free flowing. Then I can remove the ether solution from the sodium sulfate and spot a TLC plate with that solution to test for the biphenyl contamination. And I'll develop that TLC plate using methylene chloride as the mobile phase. Once it's finished developing, I'll mark where the solvent reached on the TLC plate and observe it under a UV light. The bottom spot tells us that the product definitely was formed, but we also have biphenyl contamination shown in that top spot, so we'll have to rinse the crude product with some Legroin later on. I'll evaporate the solvent using a stream of air and some gentle warming, and then begin moving the crude product over to a conical vial where I'll be adding some Legroin to dissolve the biphenyl contamination. I'll rinse it twice with about 2 milliliters of Legroin each time, making sure to break up the solid really well in order to expose all of the biphenyl to the Legroin. Then I can draw off the solution from the product and repeat the process a second time. Once dry, the crude product can be removed and transferred to a Craig tube where I'll be starting the recrystallization process. Ethanol will be used as the recrystallization solvent, and again, we want to be careful not to boil it in order to not create any unwanted byproduct. I'll start working on dissolving the product in ethanol while stirring it in the hot water bath. And there was quite a bit of crude product, so it took a lot of solvent to finally get it to dissolve, but eventually it did get there. With that much solvent in there, it is difficult for the product to come out of solution, so there's a couple things I can do to help that process. I can scratch the sides of the glass with a spatula to give a place for the solid to form, but that didn't really seem to work too well, so I'm going to go ahead and add an ice chip, and as you can see, it increases the polarity of the solution and helps the solid precipitate out of solution. So now I'll redissolve everything in the hot water bath, and it looks like I may have heated it up a little bit too much because there's this yellow solid at the bottom that's having a hard time dissolving. That might be some byproduct. But I'll leave it at room temperature now so it can recrystallize slowly. And the recrystallization process wasn't as great as I was hoping because a lot of the solid just kind of crashed out of solution. But we can see how pure it'll end up once we characterize it. After about 25-30 minutes, I put it in some ice to see if any more product would come out, but it looks like it's done now. So now I'll remove the crystals using the stopper and test tube again and centrifuge them for a few minutes. Once the crystals are isolated, we're ready to characterize now, and I'll start by weighing them out so a percent yield can be calculated. The empty watch glass is 9.735 grams, and the full watch glass is 9.782. And I'll take a melting point, starting a few degrees lower, because it did look like there might have been some contamination in the Craig tube. And this solid started melting around 161.5 degrees, so a little bit lower than the literature value, but didn't finish melting until 163.0. Finally, I'll run an IR spec using the neutral mole technique. And it doesn't look too bad. We have the sterically hindered alcohol peak, then some aromatic overtones, and a carbon-oxygen peak around 1150. So that's looking pretty good.